Hello again, this is Math 2115, Remote Alternate Delivery for April the 9th, and after a short review of some problems from the past, we'll move on and talk about some new stuff. The new stuff will include adjacency and incident matrices, and in another slice, isomorphisms. This is covering sections 8.5 and 8.6 in your book altogether. The first slice will be 8.5. Make sure you pause the video. And I want to thank you for hanging with things. Teaching and learning is possible. Grades can be earned and rendered, and your educational goals need not be deferred. So let's make some magic today. Let's stay the course, and I appreciate you helping us fight this battle. That's what champions do. Okay, so first problem, I want you to use Dijkstra's algorithm or something else to find the shortest path from node 0 to node 6. So hit pause, and I'll return and we'll see how you do. Let's see how you did. This is what you should have gotten. The path, there are many paths, but the optimal one, the shortest one was this one that weighs in at 11, and you can see it highlighted. Let's look at the same drawing of a graph, a weighted graph, but let's find a Hamiltonian cycle or show one doesn't exist. The weights really don't matter now. The only thing that matters is connectivity. I am not asking you to solve the traveling salesman problem of finding the minimum cost. The only thing I'm asking you to do is to find something that visits all vertices once except the one you start at and when you return there for home. So press pause. Let's see how you do. Okay, the graph does have a Hamiltonian cycle, and this is the one I found. There may be more, and as long as you hit every vertex once, but you start somewhere. And one way you could have done this kind of thing is you could have started at 10 and gone to 9 to 5 and so on and so forth, and then after hitting 0 you go through these. And so, but you start and end at the same place. And going back even further to what we covered, I think well into last week, can you find an Euler cycle here or show that one does not exist? Again, hit pause, please. Let's see how you did. Well, this graph doesn't have an Euler cycle because in an Euler cycle you hit each edge exactly once, and that means that each vertex has to be an even degree, and node 0 is of degree 3, and there were others that were of odd degree as well, so this has no Euler cycles. Let's talk a little bit more, and we talked about this when we were talking about Dijkstra a little bit as well. I think I used the term inadvertently, but now we're talking about an adjacency matrix, and so let's use this as an example. To obtain an adjacency matrix of this graph, we select an ordering of the vertices, and that does matter because if you change the ordering, the adjacency matrix will change. So here I'm saying let's do alphabetical order A through E. Next, we mark the rows and the columns with those vertices. So here's A through E, and here's A through E. The entry in this matrix in row I, column J, if I is not equal to J, and this is where I is equal to J through the main diagonal. So if I does not equal to J, this is the number of edges incident on I and J. Now, if I and J then have 1, that means, oh, they're connected in the graph. Now, if I equals J, the entry is twice the number of loops incident on I. And so, for example, here you see that that you do have loops that happen, and one happens at C, and I guess there are other loops where there are multiple connections happening. Okay, so notice we can obtain the degree of a vertex V in a graph by summing row V or column V in the adjacency matrix. So for example, A has degree 2 because we get 2 there, and we also get 2 if we sum across there. Now, the adjacency matrix is not a very efficient way to represent a graph. Since the matrix is symmetric, you've got a lot of wasted information and space there. And you see the upper triangle, including the main diagonal and everything above, has all the information, and this is kind of redundant. It turns out, though, that there is a bunch of applications both here and whenever we talk about isomorphisms in another slice of this video. If A is the adjacency matrix of a simple graph, the ijth matrix of A raised to the nth power, where A is the adjacency matrix, is equal to the number of paths of length n from vertex I to vertex j. There's a proof in your book. It's by induction. I'm not going to take you through that proof. It does talk a little bit about matrix multiplication here as well. But this is a theorem that it can be useful if you're asked that question: how many distinct paths of length n do exist from one to the other? I think in some of the exercises they do ask you precisely that question. The adjacency matrix will also be useful in something that we do in the next section on isomorphism. We also are introducing a thing called the incident matrix. To obtain the incident matrix of a graph, and here's the example that we're looking at, we label the rows with the vertices, those are the vertices, and the edges in some arbitrary order. So you pick, and we just call these E1, E2, E3, E4, and so on and so forth in this order. If we change this designation, we change the way the incident matrix looks, but for given this representation, this one represents this graph. A column such as E7 is understood to represent a loop. And so if you look at E7, you see E7 is indeed a loop that happens at V2. Notice that in a graph without loops, each column in an incidence matrix has two ones, and that the sum of a row gives the degree of the vertex identified with that row. Okay, let's see how we feel about this concept then. I'd like you to write the adjacency matrix for this graph, and since it matters what's the ordering, I'd ask you to use alphabetical ordering. So hit pause, do the problem, and let's see how you do. Okay, with that ordering, this is what you should have gotten as your adjacency matrix. If you didn't get this, please find out why. The next problem I'd like you to do is another problem, but this is the other way about. Instead of giving you a graph and asking you to construct the adjacency matrix, I'm giving you the adjacency matrix and ask you to show me what the graph must look like. Hit pause, and I'll return in just a bit, and we'll see how you did. Let's see how you did. This is what we started with, and you end up with a bipartite graph. We have two connected regions that are not connected with each other, and that's the connectivity you should have. Your graph doesn't have to look exactly like this, but the vertices and the connectivity has to be identical to what is shown here for it to be correct. Let's talk about incident matrix, and here what we're going to do is we've got edges, and we don't maybe know what those edges are, but this edge, for example, is connecting D and E, and there's another edge that connects D and E over here as well. So anyway, draw the graph represented by this. Hit pause, and let's see how you did. Again, it's going to be a bipartite graph, and it's going to look something like this. The connectivity and the vertices have to be the same.